Hi, this is the fourth lesson in waves. In this video, I'm going to discuss about refraction of waves. Okay, before watching this video, you can navigate to any of my lessons related to Unit 1 to 6 by using the playlist of this channel. I grouped all my 115 videos into different groups like Unit 1 lessons, Unit 1 past paper discussion, Unit 2 lessons, Unit 2 past paper discussion, and so on. So you can navigate to any of my lessons by using the playlist of this channel. Also, all the necessary and useful links related to waves and other videos are given in the description of this video. So by using the description of this video, you can navigate to the required video also. Right. So in this topic, I'm going to discuss refraction of waves. Okay. It's better to go through my first three videos before watching this fourth video, refraction. Already I discussed phase difference and the basic properties of the waves. Then in second lesson, I discussed about intensity of waves. Third lesson, I discussed one of the behavior, that is diffraction of the waves. This is another behavior of waves, that is refraction of waves. Okay, so what is refraction? In the past paper, several times this question appeared. Refraction means when a wave moves from one medium to another medium, the speed of the wave changes, and due to change in speed, the direction of motion of the wave also will change. Okay, that is called refraction. When a wave moves from one medium to another medium at the boundary, the speed of the wave will change. Due to change in speed, the direction of motion of the wave also will change. This is called refraction. Don't say the wave bend. It's not a correct way to say at the boundary the wave bends is called refraction. It's a wrong statement. Don't use the word bend. The direction of motion of the wave will change. That means when you draw, the direction of the motion is shown by ray. I already mentioned it in my first lesson. So the direction of ray will change at the boundary. But very importantly, you must know during refraction, the frequency of the wave never changes, because frequency is property of the wave, but the speed and wavelength is decided by the medium. Very important, you must know. Frequency is the property of the wave, so it remains same. How many times the wave source generates waves per second, so how many times the wave source generating wave by using vibrations or oscillations. So that is decided by the frequency of the wave. So frequency of a wave is the property of the wave, but the speed is not the property of the wave, because the same wave, when it travels through different medium, the speed will be different. So the speed depends on the medium. Therefore wavelength also depends on the medium through which the wave is traveling, but the property of the wave, which is frequency, remains same. So when a wave travels from one medium to another medium, I already explained, I already told that the wave will refract, but during refraction, the frequency will remain the same. The frequency remains unchanged. Now we'll see what's the reason for changing direction of motion. By using a simple diagram, we can explain that. Okay, so here I drew a diagram. This is the boundary of two different media, medium 1, medium 2. The speed of the wave in this medium is V1, speed of the wave in this medium is V2, V2 less than V1. We will take the speed of the same wave in the second medium is lower than first medium. What will happen? I told that frequency remains same. That means number of wavefronts approaching the boundary per second should leave the boundary per second. So I can say like this way also. When the number of wavefronts approaching the boundary per second is same as the number of wavefronts leaving the boundary per second, because number of wavefronts per second indicates the frequency. So here I took the speed of the wave in the second medium is lower than the speed of the wave in the first medium. So what happens? The wavefronts, imagine the wave, the wavefronts, the gap between the wavefronts indicates the wavelength. I already told that in my first lesson. And the ray, this is called the blue color line, is the ray. Ray indicates the direction of wave motion. So ray is used to indicate the direction of wave motion. So this is the normal to the boundary. The red color line is the normal to the boundary. The black color line, the vertical line, is the boundary between the two media, medium 1 and medium 2. Okay, so the speed of the wave in the second medium is less than the first medium, means when the wavefronts reach this one, okay, look at here, the wavefronts should continue. The wavefronts cannot be created or destroyed when they are traveling from one medium to the next medium. So the same wavefront should continue into the second medium. But what's going to happen? The second medium, it should slow down. So when the imagine this wavefront, we'll think about this wavefront. When this wavefront continues its motion in medium 1, the part of the wavefront which has gone into the, which has reached into the second medium will slow down. So when this medium slow down, the wavefront in the second medium slows down, what will happen? It will travel a less distance. Imagine this wavefront has moved from here to here. So this will move a smaller distance. So what will happen? The only possibility, it should bend like this. This also will bend like this. Now you can see that the distance moved by the second wave, the same wavefront in the second medium is less. The distance moved will be less. Or we can say according to V equal F lambda, V is decreasing, F remains the same, therefore lambda should decrease. That way also I can say. So the lambda should decrease in the second medium, means the distance between the adjacent wavefront should become smaller in the second medium. So the only possibility, the wavefronts in the second medium should turn like this. They should become like this. Straight line to draw, little difficult to draw on the board. On the notebook you can nicely draw with your ruler. So they should turn like this. So the wavefronts in the second medium should turn like this, not bending, turn. We should use the word turn. They will turn like this. Now we know that ray is a line perpendicular to the wavefront. So I can continue this one here, one more wavefront. So that also should come like this. Okay, so what happens? All these gaps are same. Here also all these gaps are same among them. But here the gaps in the second medium, the gaps are smaller than the gaps in the first medium. Because the wavelength is decreasing when we consider V equal F lambda. The second medium V is lower than the first medium. F remains the same. So lambda should decrease in the second medium. So lambda decreases means the distance or the gap between the adjacent wavefronts should become smaller compared to the wavelength in the first medium. So only possibility, the wavefronts should bend like this. Okay, so this is the normal. I already told this red color line is the normal. Wavefronts and ray are perpendicular lines among them. So we should draw the ray perpendicular to the wavefront. So at the boundary, this is the boundary where the normal and the boundary meets at this point. This is the ray of the incident wave. So I should draw the ray for the after refraction, refracted wave. I should draw a line perpendicular to the green color lines in the second medium from the point where the normal and the boundary meet. So if I draw a line, if I draw a perpendicular line, I should draw like this. So here the blue color line is the ray that is perpendicular to the wavefronts. Here also perpendicular to the wavefront. So when I draw the ray in the second medium, you can see the ray is turning towards the normal. That's the reason we, let's say, when a wave travels from medium where the speed is higher to speed is lower medium, the wave will turn towards the normal. You would have learned that in IGCSE in optics, light, is it? This is the reason we say it turns towards the normal. Okay, so the turns towards normal, the reason is the wavelength becomes smaller. So the gap between the wavefronts in the second medium should become smaller because speed is less. But the ray should be perpendicular to the wavefronts. When you draw the ray, you have to draw, there's no other option, you have to draw the line, the ray, perpendicular to the wavefronts, means it should be towards the normal. Okay, the wavefronts should be continuous because the wavefronts, those are traveling inside the first medium, should have the continuous wavefronts in the second medium also, but they should travel slowly in the second medium. So the only possibility, the wavefronts should bend, or actually bend is the wrong word I am also using. The wavefront should turn their direction like shown here. They should come to this, but they can't go like this. It can't be a wavefront like this. They have to turn like this. Same I can draw for the other situation. When the speed of the wave increases in the second medium, I'll draw that here. What happens? The ray will move away from the normal. You would have learned that already. I'll draw it now. Okay, so here I took the speed of the wave in the second medium is higher than the first medium, or the wave traveled faster in the second medium. So what happened here? I got V equal F lambda, F remains the same, second medium speed V is increasing, so lambda should increase. Lambda should increase means the distance between the next to next adjacent wave fronts should increase. So here the only possibility, the same wavefront should travel to the second medium as I explained there, right? But they should travel faster here. So if they travel faster means the only possibility they have to travel like this. They should bend like this away from it. They should travel like this. Draw it and see on a notebook. You will see the wavelength becomes larger here. When you draw it like this, the wavefront will become larger here. So here also I should draw a line that is the ray perpendicular to the wavefronts. If I draw the line perpendicular to the wavefronts, it will become like this here. Here it's perpendicular. So you can see that here when the speed increases in the second medium, the ray will move away from the normal. That's what we learned in IGCSE. When the light ray moves from glass to air, the ray will move away from the normal. This is the reason, because speed increases. Here the wavelength, the gap between the wavefronts increases. So the ray is perpendicular to the wavefronts. So here the ray perpendicular to the wavefronts means they will become the ray will move away from the normal. Okay, this is the reason. You must know, you should know this basic idea related to wavefront. So when a wave travels from lower speed to higher speed medium, the ray will move away from the normal and the wavelength will increase. When the wave moves from higher speed medium to lower speed medium, the wave will move towards the normal and the wavelength will decrease. Here it's not parallel, so that's the reason it looks small. But if you draw it on a notebook, like by using a proper ruler and everything, you will see the wavelength will increase here. Okay, so here the ray meets the boundary such the ray is perpendicular to the boundary. That means we say angle of incidence is 0. So in this situation, the ray is perpendicular, the direction of motion of the wave is perpendicular to the boundary. So there what happens, if the speed of the medium, the second one is less than the first one, the wavelength will become smaller, but there is no change in direction of motion. We can say no change in direction of motion means no refraction is occurring, but it will continue the motion along the same line of direction. So the ray, the same line we can continue. The direction of motion is not changing. It will move away from the boundary such that perpendicular to the boundary, but the wavelength in the second medium will become smaller. The wavefronts will become closer to each other compared to here. There is no refraction. Okay, so you must remember this as a conclusion. When a wave is true for all type of wave, not only for water wave or sound or light, for any type of wave this is true. During refraction, when a wave moves from higher speed medium to lower speed medium, it will move higher speed medium to lower speed medium. When it moves, it will move towards the normal. When a wave moves from lower speed medium to higher speed medium, it will move away from the normal. That is generally, you should remember that. But if the wave or the ray meets the boundary such that the direction of motion of the wave is perpendicular to the boundary, there is no change in direction of motion, so we can say there is no refraction. The wave will move along the same direction as earlier. Okay, so in your syllabus, most of the questions related to refraction are related to refraction of light. Okay, so when we consider refraction of light, we use a word called refractive index of a medium, but actually that should be absolute refractive index of medium. So how do you define the absolute refractive index of a medium? Means, you know, I already told that speed of light will be different in different medium. The highest speed of light is in vacuum, which is almost 3 into 10 to the power 8 meter per second. We can take it 3 into 10 to the power 8 meter per second. That's the way the value is given in the data sheet. So we can say the speed of light in vacuum is 3 into 10 to the power 8 meter per second. So absolute refractive index of a medium is defined as the ratio of speed of light in vacuum to speed of light in the medium. But in this syllabus, we don't use the word absolute. We use refractive index. That's all we use. Refractive index of glass, refractive index of water. But it should be absolute refractive index of water, absolute refractive index of glass. Such we normally the books, they define the refractive index as in terms of absolute refractive index, but it's okay, no problem. We can use, instead of absolute refractive index, we can use the word refractive index, right? So refractive index of a medium is defined as refractive index of a medium is defined as speed of light in vacuum divided by speed of light in the medium medium or material. So it's denoted by N is equal to C over V. So this is the definition of absolute refractive index, but we don't use the word absolute. So this is definition of refractive index. Speed of light in vacuum, which is 3 into 10 to the power 8 meter per second. We know that this is 3 into 10 to the power 8 meter per second, divided by speed of light in the medium. Say for example, if you are finding the refractive index of glass, I can denote Ng, no problem, I can use that word. Books, they use Ng, refractive index of glass means absolute refractive index of glass, but we use the word refractive index of glass is equal to speed of light in vacuum divided by speed of light in glass. Same way, absolute refractive index of water in W, speed of light in vacuum divided by speed of light in water. So always the refractive index, that is the absolute refractive index, will be more than or greater than 1, because normally the speed of light is the maximum or highest in vacuum. So the speed of light in glass or speed of light in water is lower than the speed of light in vacuum. So when you find this fraction or decimal value, it will be greater than 1. So always the refractive index will be greater than 1. And also you must remember, this is the ratio of the speed. So same units. So refractive index has no unit. So one more thing you should know, that if the refractive index is higher, that means the refractive index is higher means the speed of the light in that medium is lower. If the refractive index is lower, when you compare two different media, the refractive index of two different media, so if the refractive index is higher for a one medium, that means there the speed of light is lower. If the refractive index is lower means speed of the light in that medium is higher. That's the meaning. Say for example, I can compare like this. We'll consider two media X and Y. Say medium X, medium Y. So medium X, medium Y. So the speed of light in medium X is Vx, speed of light in medium Y is Vy. Nx, that is the refractive index, Nx equals C over Vx, Ny equal C over Vy. So very simple mathematics. If I say Nx, refractive index Nx is greater than Ny, that means Nx greater than Ny means a Vx, the speed of the light in that medium is less than speed of the light in the second medium Y. The other way, if I say Ny less than Nx less than Ny means, that means the speed of light in the medium X is smaller than Y means the Vx is larger, Vx greater than Vy. Better to know these things because there could be statements in the MCQ. Okay, so what could be the refractive index of air? How to define the refractive index or the absolute refractive index of air? That is speed of light in vacuum divided by speed of light in air. But you know the speed of light in air is very closer to the speed of light in vacuum because density of air is very low. So when you calculate the actual value, the speed of light in vacuum divided by speed of light in air, you will get 1.00027. So it's very closer to 1. So if your syllabus we take the refractive index of air equal to 1, that is the medium with lowest refractive index. All other media have refractive index greater than 1. I already told that. We take the refractive index of air is equal to 1 in your syllabus. Okay, so these two words are used related to reflection of light in your syllabus, or even IGCSE will use these things, these two sentences. Optically more denser medium, optically less denser medium. What do you mean by this? Normally when we compare two different media, we use that. For example, imagine we compare two different media X and Y. So the speed of light in X, let it be Vx, this is Vy. So when we compare these two media, X and Y, if the speed of light is more in a medium, we call that optically less denser medium. If the speed is more compared to the another medium, we say that medium which has higher speed of light, we call it as optically less denser medium. So if, for example, if I say Vx greater than Vy, the speed of light in X is greater than speed of light in Y means Vx is optically less denser medium. So if the speed is higher, optically less denser medium, or I can say the speed of Y is less than, the speed of light in Y is less than the speed of light in X means this is optically more denser medium. So if the speed is higher, we call that medium optically less denser medium. If the speed is less, we call optically more denser medium. Also, we can compare in terms of refractive indexes. So if the speed of X is greater than speed of light in Y means, you know, according to the definition N equals C over V. So speed here is more means Nx is going to be smaller than Ny. The speed is more means the refractive index of S will be smaller than the refractive index of medium Y. So remember that the optically less denser medium will have smaller refractive index. Optically less denser medium means speed is more, that will have smaller refractive index, and optically more denser medium has smaller speed of light that will have greater or larger refractive index. So generally I can say a medium with higher refractive index is optically more denser medium where the speed of light is lower. Uh, a medium that has smaller refractive index is optically less denser medium in which the speed of light is higher. Remember that. Next thing is Snell's law. Snell's law relates refractive index of two different media at the boundary and the angle of incidence and angle of refraction. We don't need to use those words when we use here this Snell's law. It's easy to explain like this. There are two different media. This is medium 1 and this is medium 2. The speed of light here is V1, speed of light is here V2. Whether V1 greater than V2 or V2 greater than V1 is not important here. So imagine the light is moving from medium 1 to medium 2, or just it's passing the boundary, and here the angles are always measured with the normal. So if the angle here with the normal is theta 1, here theta 2. I don't want to say angle of incidence, angle of refraction. At the boundary, the light ray is crossing the boundary from one medium to the next medium. In the first medium, it's making an angle theta 1 with the normal. In the second medium, it emerges or moving away from the boundary such that its angle with the normal is theta 2. The refractive index of medium 1 is N1. This refractive index is N2. So the Snell's law, it could be proved, we can derive it, but we don't need the derivation. The Snell's law says that N1 sine theta 1 is equal to N2 sine theta 2. So here we don't need to consider from where to where the light is moving. Whether it's moving from 1 to 2 or 2 to 1, we don't need to consider. Even if the light ray, if I invert the direction like this, even if I invert the direction like this, the same equation is valid. The same equation is valid even if I invert the direction. But very important, the angles theta 1, theta 2 must be measured with the normal to the boundary, because this equation was derived by using similar triangles, geometry, purely by using geometry and the similar triangles. So during the derivation, the angles with the normal are considered. Even if the angles with the boundary given, we must consider, or we must use the angles with the normals here. So whether the light is moving from medium 1 to medium 2 or medium 2 to medium 1, we don't need to worry. Simply I can say N1, the medium, the refractive index of a medium into the angle with the normal to the boundary in that medium. Sine of the angle in the at the boundary with the normal, that is equal to refractive index of the next medium into the angle with the normal to the boundary in the next medium. So it's very simple equation to use. IGCSE you use n equals sin I over sin r. We don't need to consider such format here. We don't need here actually. We can use this one for any question related to refractive index. So n1 sin theta 1 equal to n2 sin theta 2. n1, n2 are the refractive index of the two media. Theta 1 is the angle in the medium which has refractive index n1, and this angle is measured with the normal to the boundary. Here the same way, theta 2 is the angle with the normal to the boundary in the medium which has refractive index n2. If it is air, for example, if the light is, one of the medium is air, for example, whether one of the medium is air, then we substitute 1 for the refractive index of air. I already told that the refractive index of air is taken as 1. So we substitute refractive index of air 1 in that for that particular question. There we put the n as 1 for the refractive index of air. So we can summarize what we learned so far. The refractive index or absolute refractive index of a medium is defined as n equals c over v. That is, c is the speed of light in vacuum divided by speed of light in the medium. That's the refractive index or absolute refractive index of the medium. First, you must know that. The second, you should know for air, the refractive index, we take it as 1. Then the next equation, Snell's law, n1 sine theta 1 equal to n2 sine theta 2. Then you should know the medium that has the speed of light is compared to another medium. The speed of light is higher in a medium. The speed of light is higher means we call it as optically less denser medium. Optically less denser medium means the refractive index will be lower for that medium. Optically more denser medium means that has a speed of light in that medium will be lower and the refractive index will be higher. Also, I already explained during the start of this lesson, when a wave moves from one medium to another medium, if the speed decreases in the second medium, it will move towards the normal. If the speed increases in the second medium, it will move away from the normal. That also you must know. Okay, now we'll do few questions, exam style questions related to what we learned so far. Okay, first question, very simple question. Refractive index of glass is 1.54. Find the speed of light in glass. So we know that according to the definition, refractive index of glass is equal to speed of light in vacuum divided by speed of light in glass. This is 1.54 equal to 3 into 10 to the power 8. That's given in the data sheet. 3 into 10 to the power 8 divided by Vg, speed of light in glass. So speed of light in glass, divide this by this, you will get 1.95 10 to the power 8 meter per second. Okay, second question, light rays moving from air to glass, angle of incidence with the normal in air is 42 degree. Find the angle of refraction in glass. So the refractive index of glass is given Ng is equal to 1.53. Okay, so we know that refractive index of air is 1. So we'll use the equation n1 sine theta 1 equal n2 sine theta 2. That is the Snell's law. So n1 theta 1, they should be the similar. The angle with the normal in the medium 1 is theta 1. So n1 air, the refractive index is 1 into sine 42 equal, the refractive index of glass is 1.53 into sine theta 2 with the normal is r. That's a question. Angle of refraction, sine r. So sine r is going to be sine 42 over 1.53. So solve it for r. So you will get 0.437. So find that, take the inverse sine, that will be 25.9 degree. Okay, so this is the third question in which the light ray is moving from glass to water. The angle is given with the boundary. Here the question is they asked to find the angle theta. So I told that we need to use, when we are using Snell's law, we must use the angle with the normal. So here the refractive index of glass is given 1.54, refractive index of water is 1.33. So I need to find the angle with the normal when I use the Snell's law. Then I can find this angle. Then 90 minus this angle, what I am going to find will be equal to theta. That's the first part. Second part, I'll come to that point about angle of deviation. Okay, so if you are using this Snell's law, theta 1 is equal to that. Normally we use, n1 sine theta 1 equal n2 sine theta 2. So I will find the theta 1. That is going to be this angle. If I say this angle theta 1 is equal to 90 minus 38. So that will be 52 degree. So I'll use the equation n1 sine theta 2 is n1 sine theta 1 equal to n2 sine theta 2. So I'll say this angle theta 2. I'm going to find the theta 2 first. So n1 1.54 into the relevant angle sine theta 1, that is sine 52, is equal to N2, that is water, 1.33 into sine theta 2. Okay, so I need to find the sine theta 2 here. So that is sine theta 2 will be equal to, solve it, sine theta 2 will be equal to 1.54 into sine 52 divided by 1.33, that will be equal to 0.912. So theta 2 will be equal to 65.8 degree. Theta is the question. Theta, this theta is equal to 90 minus theta 2. 90 minus 65.8 degree, that will be 24.2 degree. Okay, second part, find the angle of deviation. So the angle of deviation means if there is no change in medium, if there is no boundary, if both are the same medium, the light ray would have gone this way. So the light ray would have moved this way. But now it's moving like this, means this is the angle of deviation. This amount is the angle of deviation. It would have gone this way, but it's now going this way, means the amount of change in angle is this one. We need to find this angle, the amount of deviation, how much it deviates from its actual path. The initial path is this way, it would have gone this way if there is no change in medium. But due to the change in medium, it has changed its direction of motion, or it has changed its direction of motion due to refraction. So the angle of deviation means this is the angle of deviation, how much it deviated from its actual path or initial path. So I need to find this angle. So we know this is 38 degree. So that means this we found it already in the first part. This is 52 degree. We found it, this one in the first part, 52 degree. So if this is 52 degree, so you know this is the opposite angle. This will be 52 degree. This also 52 degree. But we found the angle of refraction. The whole angle we found. This angle we found it already. The whole angle from here to here. We found this angle already. That is 65.8. So the angle of deviation is this angle. So angle of deviation, second part. This part, the angle of deviation, we need to find this angle. So the whole angle, this is 65.8, this is 52. So that will be 65.8 minus 52. So that will be 13.8 degree. We can say clockwise if you want, but normally you don't say. If you want, you can say the angle of deviation 13.8 clockwise direction. Okay, fourth question. There are two different media. Medium 1, the speed of light is 2.40 10 to the power 8. Medium 2, the speed of light is 1.92 10 to the power 8 meter per second. The light ray is reaching the boundary at 36 degree angle of incidence with the normal 36 degree. The first part, draw the ray in medium 2. You know the light is traveling from this is higher speed to lower speed, optically less denser medium to optically more denser medium. Means you know when light travels from optically less denser medium to optically more denser medium, it will move towards the normal. We should draw it's moving towards the normal. So this is going to be angle of refraction, R. That's the second part they asked to find it. I can use the Snell's law in one. So second part, first part I done is completed. I drew the diagram. The ray will move towards the normal. Second part, I need to find the angle of refraction in the medium 2, the second medium. N1 sine theta 1 equal N2 sine theta 2. Right, that's a equation given by Snell's law. So N1 means here the refractive indexes are not given, the speeds are given. We know the speed of light in vacuum is 3 into 10 to the power 8. N1 means the speed of light in vacuum divided by speed of light in medium 1 sine theta 1 equals C over V2. N2 means C over V2 sine theta 2. Right, we'll continue. C and C will get cancelled. 1 over V1 sine theta 1 equal 1 over V2 sine theta 2. The theta 1, theta 2 should be with the normal to the boundary. So 1 over V1, the first medium, 2.4 10 to the power 8. So 1 over 2.4 10 to the power 8 sine, the angle with the normal is 36 degree equal to 1 over medium second one, 1.92 10 to the power 8 sine theta 2 with the normal is R. That's a question, angle of refraction. I need to find the sine R and I have to finally find the R. Solve it. Make the R sine R subject. So sine R will be equal to, you will get 0.470. So R will be equal to 28 degree. Okay, so this is the fifth question. Light rays moving from medium 1 to medium 2. The diagram is given here. Both angles are measured with the boundary, not with the normal to the boundary. So we need to find the angle with the normal to the boundary. So let this angle be theta 1. This is theta 2. So theta 1 is equal to 90 minus 43. So that will be 47 degree. Theta 2 will be 90 minus 58. So that will be 32 degree. So the question is find the speed of light in second medium. This speed is given in the first medium 2.84 10 to the power 8 meter per second. Anyway, we are going to use the same equation, Snell's law. N1 sine theta 1 equal N2 sine theta 2. N1 means C over V1 sine theta 1 equals C over V2 sine theta 2. C will get cancelled on both sides. So 1 over V1 sine theta 1 equal 1 over V2 sine theta 2. So we'll substitute the known quantities. 1 over V1 2.84 10 to the power 8 sine theta 1 we found it 47. 1 over V2 I need to find the V2 sine 32. Solve it, you know how to solve this. Make the V2 subject, you will get V2 is equal to 2.06 10 to the power 8 meter per second. That's the speed of light in second medium. Okay, so this is slightly different type of question, little bit of geometry we need to use and also an extra equation is given. You would have done it in maths, sine 90 minus theta equal cos theta. Okay, so we'll take this angle. So the question is find the refractive index. So it's a cuboid. So the opposite sides are parallel and these angles are 90 degree. And angle of incidence in the air, the surrounded by air, this is a transparent material, not glass, something else, but transparent cuboid. This angle is 72 and the light is emerging at an angle 53 with the normal in the next medium. Okay, so the question is find the refractive index. So this is normal to this side, this is normal to this side. We'll make this angle theta 1. So before that we'll extend these lines. If we extend this normal and this normal, it will form this angle will be 90 degree in this triangle. Okay, we can take this angle theta 1, this angle theta 2, or I will take this angle r. This angle r, if I take, this will be in this triangle, right angle triangle, this is r, this is 90, means it's going to be 90 minus r. That will be 90 minus r. This is 90 degree in this right angle triangle, this is r, this will be 90 minus r. Okay, so for this boundary, we'll use, if you want, you can name it A, B, C, D. The names we can name the sides of the cuboid. For the boundary AD, if I use Snell's law for the boundary for AD, if I use Snell's law, n1 sine theta 1 equal n2 sine theta 2. That's a Snell's law. n1 air, which is 1 into sine theta 1, 72, sine 72. n2 is the question, we'll name it n. That's the question, we need to find the refractive index of the glass. n2, that is n into sine r. So n is equal to, n will be equal to sine 72 over sine r. Okay, so same way, we'll use for this boundary AB. For the boundary AB, we'll use Snell's law. If we use Snell's law again, so n1 sine theta 1 equal n2 sine theta 2. n1, that is inside the glass, light is going from here to here. So I'll say n1, that is n1 sine theta 1 equal n2 sine theta 2. Anyway, that's the equation, general equation. n1 means I'll take the medium inside the glass, that is n sine theta 1 with the normal, that is 90 minus r. n2 is the second medium I'm using for this boundary. So second medium, that is air, which is 1 into sine 53. So if I make the n subject here, n is going to be sine 53, because 1 into sine 53 is sine 53 over sine 90 minus r. But here they have given a relationship, sine 90 minus theta equal cos theta. So sine 90 minus r equal cos r. So I can write this as n equal, so I'll continue here, n equal sine 53 over cos r. Keep it as second equation, this is first equation. Okay, when we consider first equation and second equation, the left side is the same quantity, refractive index. Therefore, the right side should be the same. So, therefore, when I consider the first equation and second equation, sine 72 over sine r equals sine 53 over cos r. Okay. Nothing hard, but little bit of math coming. I just put this question. Okay, we know sine theta or cos theta equal tan theta. We use that in unit 1. When we use that in unit 1 projectile, unit 1 forces. So we'll rearrange this equation. So bring this sine up here, sine 53 here. So sine 72 over sine 53 is going to be sine r over cos r. So this you can find it from the calculator. You know the values of sine 72 and sine 53. If you solve that, you will get 1.191 sine r over cos r tan r. Now find the r, tan inverse, take it and find the r. You will get almost 49.98, 50 degree. Okay, you know the r now, 50 degree. Substitute this r in one of the equation, either here or there, wherever you like you can substitute. You will get the refractive index. So if I use the first equation, so I put a line here, n equal, I am using it in the first equation, n equal sine 72 over sine 50. If you want, you can use this r here also, you will get the same answer. Solve it, you will get the refractive index 1.24 for the transparent material. Just answer. Little too much of work. So far no such question, but just nothing new to you. Only thing, using this equation, a little bit of math comes, that's all. Okay, so question number 7, you can answer, but slightly here also we use little bit of maths here, mathematics here. Okay, so this is a prism. The refractive index of the glass of the prism is 1.52. The angle of the prism angle is 60 degree. The angle of incidence of the ray is 40 degree. This is the normal to the side. This is the normal to this side. The question is, find the angle of refraction theta in the second face or second side. Okay, so we know these two are normal to the boundary, and we know the total angle inside a quadrilateral shape will be 360 degree. Okay, so we'll use the Snell's law. Here we'll make this angle theta 1, or we'll say this is R1, this is R2, no problem, we'll use that way. And we'll extend these normals. When we extend these normals like this. Okay, so here we can name the sides if you want. We can name it A, B, C. Okay, on the face AB, we use the Snell's law. For the side AB, we use the Snell's law. N1 sine theta 1 equal N2 sine theta 2. So it's kept in air. So the outside is air. So the refractive index is 1. So N1 is air, that is 1 into sine 40 is equal to N2, that is the prism angle, the refractive index of the prism, 1.52 sine R1. We'll find the R1. So sine R1 will be equal to that will be equal to 0.423 0.423. So R1 will be equal to 25 degree. Find it sine inverse. You will get R1 25 degrees. Okay, so we'll find this angle. This angle we will find it. So in this quadrilateral shape, the total addition of the angle will be equal to 360 degrees. So this is 90 degree. This is 90 degree. We need to find this angle. We'll call this angle alpha. This angle we'll call alpha. This angle, the angle between the two normals, we'll find that alpha. So in this quadrilateral shape, the total addition of the angle inside is 360 degree. This is 90 degree. This is 90 degree. This is 60 degree. We need to find the alpha. So we know that alpha plus 90 plus 90 plus 60 equal to 360. alpha, this is 90 degree because this is normal to this side, so alpha plus 90, this is also normal to this side, so 90 plus 60 is equal to 360 degree. We'll find the alpha, so alpha will be equal to 120 degree. Okay, so in this triangle, we know this is 120. This R1 we find in 25 degree. We need to find the R2. So R1 plus R2 plus alpha 180. So R1 we know that, which is 25, plus R2 plus 120 equal to 180. So we need to find the R2 now. R2 we need to find it. That is the angle with the normal at the second phase. So R2 will get 35 degree. Okay, so now you know the angle of incidence at the second phase. Now use the Snell's law for the boundary AC. For the phase AC, use Snell's law. N1 sin theta 1 equal N2 sin theta 2. N1, which is inside the glass, the angle is with the normal 35 degree. N1 is 1.52, 1.52 sin R2, that's the angle of incidence for this phase, that is 35. In the air, N2, here air for the phase AC I am using, so this is 1 into sin theta 2 is theta, I need to find sin theta. So sin theta will be equal to, you will get sin theta will be equal to 0.872. So theta will be equal to 60.73. Again I'll explain. So I use the Snell's law for the first phase. The given data in this question is the prism with angle 60 degree is the prism angle. Angle of incidence on the first side is 40 degree. The question is the angle of refraction in the second phase. That's the question. Okay, so this is 60 degree. I use the Snell's law for the first side AB. N1 sin theta 1 equal N2 sin theta 2. N1 is the medium air. So the first medium air, so that is 1. Sin theta 1 with the normal 40 degree, that is given in this question. So sin 40 equal. N2 is the glass of this prism, the medium, which is 1.52 sin R1. R1 is the angle of refraction for the first phase AB with the normal. The red color line is a normal. This is R1. So we find the R1 25 degree. Then I need to find the angle of R2. For that, in this quadrilateral shape, the total angle or the addition of the angle inside the four sides should be equal to 360 degrees. So 60 degree. This is 90 degree because the red color line with the black color side 90 degree. Here also red color line and the side is 90 degree. So 60 plus 90 plus 90 plus alpha, that is equal to 360 degree. I found alpha 120 degree. Now I am using a triangle, this triangle, consider this triangle here. This triangle is clear. That's this ray, this red color, this red color. So in this triangle, alpha plus R1 plus R2 180 degree, R1 plus R2 plus alpha 180, R1 we found it 25 degree already here, alpha we found it 120 degrees, so we are finding the R2 35 degree. Now I am using the Snell's law for the side AC again. N1 sin theta 1 equal N2 sin theta 2. So like N1 for this medium, that is glass, which is 1.52, sin 35, R2 is the theta 1, that is 35 degree, equal to N2, the medium outside is air, so refracted as 1 into sin theta. I need to find the angle theta with the normal. Solving will get a 60.7. Little hard, but better know that this type of questions also. Okay, so the next topic is critical angle and total internal reflection. Okay, we know that when light moves from, or light ray moves from optically more denser medium to less denser medium. More denser medium means where the speed of the light is lower Optically less denser medium means the speed of the light is higher. Or another way I can say optically more denser medium means refractive index is higher. Optically less denser medium means refractive index is lower. Okay, so when light moves from optically more denser medium, let it be medium 1 to medium 2. So the speed here V1, here speed V2, let it be V2 greater than V1. So that means optically more denser medium, optically less denser medium, right? So there when light moves from optically more denser medium to optically less denser medium, the light ray will move away from the normal. So if I say this angle is I or theta 1, this will be theta 2. Okay, so here the explanation is, you know that in trigonometry when theta increases, sine theta will increase. When theta increases, sine theta in the first quarter within 90 degrees, 0 to 90 degrees, the sine theta also will increase, or the other way, when sine theta increases, theta will increase within the first quarter from 0 to 90 degrees. So here we know according to Snell's law, n1 sine theta 1 equal to n2 sine theta 2. So the refractive index of first medium is n1. Refractive index of second medium n2. n1 sin theta 1 is n2 sin theta 2. For a given medium, the refractive index is constant because speed of light is constant in that medium, it won't change. So the refractive index of a medium is constant. So n1, n2 both are constants. So what happens when theta 1 increases? When I increase the angle of incidence, which is measured with the normal, that I use the notation theta. When theta 1 increases, n1 is constant, theta 1 increase means sin theta 1 will increase. So the left side quantity, the total left side quantity, that is n1 into sin theta 1 will increase. On the right side, n2 is constant, but when the left side increases, sin theta 2 also should increase. That means theta 2 should increase. But already theta 2 greater than theta 1. Here we know this is optically optically more denser medium. This is less denser medium. So we know that theta 2 greater than theta 1. When theta 1 increases, theta 2 also will increase to satisfy this equation. So, which angle will become 90 degree first? Theta 2 will become 90 degree before theta 1 becomes 90 degrees, because already theta 2 is larger than theta 1. When theta 1 increases, theta 2 also will increase. Both will increase, but theta 2 is already greater than theta 1. So, theta 2 will become 90 degree before theta 1 becomes 90. This particular angle of theta 1 at which theta 2 becomes 90 degree is called critical angle. So that means when light travels from optically more denser medium to less denser medium, for a particular angle of incidence in the less denser medium, the angle of refraction in the more denser medium becomes 90 degree. This particular angle of incidence in the less denser medium is called critical angle. So they are at critical angle. If I draw the diagram, this is N1, this is N2 refractive index. We know that optically more denser medium, less denser medium, N1 greater than N2. So this is less denser medium. So when light travels from optically more denser medium to less denser medium, for a particular angle of incidence, the angle of refraction theta 2 becomes 90 degree when theta 1 has a specific value we call critical angle denoted by C. Okay, so I told that when theta 1 increases, theta 2 will increase, but theta 2 will become 90 degree before theta 1 becomes 90 degree. When theta 2 becomes 90 degree, the angle of theta 1 is called critical angle, that is denoted by C. So I'll put C here. This theta 2 has become 90 degree. Okay, so here neither is air. The question in IPCSE, one medium is air. So there you already had these ideas in IGCSE. You use sin c equal 1 over n you use, but careful, don't use this equation in year 12 questions papers, because this is true only when one medium is air. In IGCSE, whenever there is critical angle or total internal reflection, I'm going to come back to that point. Total internal reflection questions comes, one medium is certainly air, but in A level, you can't expect one medium to be air. Neither is air. It could be two different media. Maybe this is optically more denser medium, which is glass 1.52, optically less denser medium water 1.33. Neither is air. So there, when you are using the equations, careful, don't use sin c equal 1 over n. Better approach the method I am going to do now. So they are nothing new. We use the same equation, Snell's equation. Only thing, we put theta to 90 degrees. So here I can use this situation where the critical angle causes angle of refraction 90 degrees. So I am going to use the Snell's law, nothing new, the same one, n1 sin theta 1 equal to n2 sin theta 2. The same thing what we learned already. So there n1 is the first medium, optically more denser medium, n1 sin c. Now theta 1 has become critical angle, sin c, n2, the second medium, sin theta 2 is 90. So into sin 90. Nothing new. So you can find the critical angle. If you know the absolute refractive indexes, that is, in your word absolute is not used. So refractive indexes of two media, optically more denser medium, optically less denser medium. If you know both n1 and n2, you can find the angle C by using this, because we know sin 90 equal to 1. So n1 is sin C equal to n2. Sin 90 is 1. So sin C equal n2 over n1. So if you know n1, n2, you can find the C. Don't use 1 over sin C, or sin C equal 1 over n, don't use. That is true only when the second medium air. Okay, you can get that same equation if it is air. N2, if this is air, if this medium is air, n2 will be equal to 1. Okay, so if the second medium is air, n2 will be equal to 1. So you will get sin C equal 1 over n1. That's the equation used in IGCSE. But here we don't use that, because that is true only when the second medium is air. So better use this format. You can start with the Snell's law and proceed with put the second angle 90 degree and continue with this format. You will come across the correct answer. Okay, so one more thing you must remember, critical angle is not the property of the one medium. It's a property of the boundary, depends on both media, because I already showed that sin n1 sin theta 1 equal n2 sin theta 2. So when it becomes critical angle in the optically more denser medium, theta 1 will become C. So n1 sin C equal n2 optically less denser medium sin 90. Theta 2 is 90 degrees, sin 90. So sin 90 equal 1. So sin C equal n2 over n1. So if you take the C, that will be sin inverse n2 over n1. So the angle of critical angle C depends on both refractive indexes, not one refractive index. So remember that critical angle is not the property of one medium, it's the property of the boundary. We never ask find the critical angle of glass, find the critical angle of water. We ask find the critical angle for glass water boundary or glass air boundary, or critical angle of medium 1, medium 2 boundary. That's the way we should ask, because it's a property of the boundary, not the property of one particular medium. Remember that. Okay, so then what is total internal reflection? So when the angle of incidence becomes critical angle, when light moves from optically more denser medium to optically less denser medium, n1 greater than n2. So optically more denser medium, optically less denser medium. When the angle of incidence is equal to critical angle, the angle of refraction becomes 90 degree. But if the angle of incidence slightly increases, even half a degree or even 0.5 degree or 0.1 degree increases more than critical angle, light can't emerge into the second medium. then what will happen? Light will reflect back. All the light will reflect back. That is called total internal reflection. No light will emerge into second medium when the angle of incidence becomes greater than critical angle. So greater than critical angle means critical angle may be, for example, if the critical angle is 30 degree, if the angle of incidence become 30.0001 degree, slight increase will make it to uh, have a total internal reflection. So there's a practical we can do. We can increase the angle of incidence gradually, slightly. Initially angle of incidence is theta 1. Increase the angle of incidence little by little. At a particular angle, when the angle theta becomes C, critical angle, you will see all the light will emerge along the boundary. Very difficult to get it, but practically if you carefully, slightly, slowly increase the angle of incidence from theta 1 at a particular angle C, all the light will move along the boundary. When it becomes slightly more than C, even half a degree, 0.1 degree, 0.01 degree, slightly more than C, all the light will reflect back into the optically more denser medium. That is called total internal reflection. So when you gradually, step by step, slowly when you increase, if the total internal reflection occurs, I can say this angle is equal to C, because slightly you increase, little more than the critical angle. So it shows complete reflection, total reflection. So during total reflection, it obeys or follows the law of reflection. Angle of incidence is equal to angle of reflection. So this also will be equal to angle of incidence. So if, for example, if C is 25 degree, it slightly increases, 25.001 degree also will cause total internal reflection. So 25.001 is approximately equal to 25 degrees Celsius, 25 degree. So I can take this as critical angle when slightly I increase more than critical angle. Okay, so if it is more than 25 degree, if it is become 35 degree, yes, no problem. Now C has become, the angle of incidence has become more than 25, maybe 35 degree, then total internal reflection, this also 35 degree. Okay, so when the angle of incidence become little more than critical angle, total internal reflection will occur. If it is much more than critical angle also, total internal reflection will occur. During total internal reflection, it follows or obeys the law of reflection. Angle of incidence is equal to angle of reflection. So why do we use the word total internal reflection? No light will emerge into the second medium. But other than critical angle, during all refraction, even during refraction, when the angle of incidence is less than critical angle, so there will be light emerge into second medium. This is N1, N2, N1 greater than N2. If the angle of incidence is less than critical angle, we know that light will emerge into the second medium theta 1. It will move away from the normal theta 2, but there will be partial reflection. A very small amount of light could reflect. So always during refraction, there could be a partial reflection also with theta 1. That also can happen. When we do questions related to refraction, we don't consider this one because we don't need that reflected light. The reflection happens always even when there is refraction. So when theta 1 less than critical angle, there will be light emerge into the second medium, but a small portion of the incident energy, incident light will have a partial reflection. During that partial reflection also there will be, it obeys the law of reflection. But total internal reflection means no light emerge into second medium. All the light will totally reflect back to the first medium. That is called total internal reflection. Total internal reflection used in optical fibers. So there are always angle of incidence at the boundary of coke cladding will be more than the critical angle. So there will be total internal reflection happens inside the optical fiber without loss of any light or energy. Okay, so we'll do a few questions related to critical angle and total inner reflection. So find the critical angle for glass air boundary. I told that critical angle is not a property of one medium, it's a property of the boundary. So find the critical angle for glass air boundary. I already told that it's better not to use sin c equal 1 over n what you use in IGCSE. We'll use the equation what we learned Snell's law n1 sin theta 1 equal n2 sin theta 2. So we know that refractive index of AI is 1. This is 1.52. Larger refractive index means optically more denser medium, optically less denser medium, glass air boundary. So there, where in which medium critical angle will occur inside the glass? The critical angle always occurs inside optically more denser medium when there is a boundary between more denser medium and less denser medium. So critical angle will occur inside the optically more denser medium, which is glass. The other medium is air. So this becomes 90 degree n2. Okay, we'll use n1 sin theta 1 equal n2 sin theta 2 for the glass air boundary. We are going to use that. n1 is the optically more denser medium. From that, light is trying to emerge into air. We'll see what's the critical angle. So n1 is ng, the glass, ng sin c equal n air times sin 90. The critical angle occurs in the glass, so the angle theta 2 will become 90 degree in optically less denser medium. So Ng, we know that 1.52 sin C equal N air 1 sin 91. So solve it now. Sin C equal, you get same format as IGCSE, but better follow this way. 1.52. Find the C. So you'll get C is equal to critical angle 41.1 degree. That's a critical angle for glass air boundary. Okay, so in this question, the speed of light in water is given 2.26 10 to the power 8 meter per second. The other medium is air. We know that speed of light in air is 3 into 10 to the power 8 meter per second. So optically, more denser medium, less denser medium. So the critical angle will occur inside the optically more denser medium, that is inside water. So the light moves from optically more denser medium to less denser medium. So this is 90 degree. So this will be the angle C, critical angle C. Okay, so the refractive index is not given. So what is the given quantity? Speed of light in water. Speed of light in air, we know 3 into 10 to the power 8, no problem. Here also we can use the Snell's law, the equation n1 sin theta 1 equal n2 sin theta 2. n1 means speed of light in vacuum over speed of light in first medium, that is in water. Sin C, the critical angle occurs inside water. N2, speed of light in vacuum over speed of light, speed of light, N2, we know, I don't need to substitute, N2 we know speed of the refractive index of air is 1, sorry, that is 1 into sin 90. So careful, this is C stands for speed of light, this C stands for critical angle, don't get confused, same notation. So this C is 3 into 10 to the power 8, speed of light in water 2.26, 10 to the power 8, sin C equal 1 into sin 91, 1. So solve it, sin C equal 10 to the power 8, 10 to the power 8 will get cancelled, 2.26 over 3. Find the C, critical angle. You will get the answer 49.9 degree. Okay, so here are two different media. One is a transparent sheet 1.64, glass 1.52. Find the critical angle for this boundary. They didn't say whether it's a glass transparent sheet or transparent sheet glass. So from where to where light goes, there could be critical angle, total inner reflection occurs. So they didn't say that, but we can find which in which medium, inside which medium there could be critical angle. Remember that critical angle occurs inside optically more denser medium. Optically more denser medium means refractive index is more. So here the refractive index of plastic transparent sheet is 1.64, which is more than 1.52. So the critical angle will occur inside the transparent sheet. So if I draw the normal here like this, and if the light emerges from transparent sheet to glass like this, the critical angle will occur inside this one, and the light will move along the boundary here like this. So this is the angle 90 degree in the medium, second medium. Always critical angle occurs inside the optically more denser medium, is where the refractive index is more. So I need to find the critical angle for this boundary, means transparent sheet, glass boundary. Light should move from transparent sheet to glass, then there will be critical angle inside the transparent sheet, because that is optically more denser medium. So we'll use the equation, Snell's law, n1 sine theta 1 equal n2 sine theta 2. n1 is 1.64, sine c equal n2, that is for the glass, that is 1.52 sine 90. Okay, so sine c will be equal to sine 91, 1.52 over 1.64. So that will be sine c equals 0.927. So the critical angle 0.927, that will be equal to 67.97 degrees. So C will be 67.97. So I can say 68 degree, 68 degree approximately. Okay, so this is a triangle. This is 90 degree, 45 degree. The light ray is the side AC kept vertical, and the light ray is entering such that it's perpendicular to the side AC. What will happen to this light ray? Okay, so what's the angle of incidence? So this is 45 degree, this is 45 degree, this is 90 degree, because this is vertical line. So the question is, what will happen to this light ray? We can't answer without doing proper calculation. So we'll do the calculation to find the angle of incidence on the side AB. So this is 45 degree, this is 90 degree, means this is 45 degree. But the normal, which is perpendicular to the side AB, that is 90 degree. So this is 45 degree, the whole thing is 90 degree. This angle also 45 degree. Okay, so when the angle of incidence on the side AB, which is glass air boundary, the angle of incidence is 45 degree, will the light emerge into air, the surrounded by air, this is air, will the light emerge into air, or will there be total inner reflection? So we need to find the critical angle first. The refractive index of the glass is given 1.52. So we'll use the Snell's law, n1 sine theta 1 equal n2 sine theta 2. At the boundary, glass air at AB, we are going to use this equation to find the critical angle. So anyway, critical angle for glass air, I don't need to say the boundary which one. So glass air boundary, optically more denser medium, less denser medium. N1 is the refractive index of glass, which is 1.52. Sine C, the critical angle occur inside glass. We will see the critical angle first. Then we will compare the 45 degree angle of incidence on AB. Here there is no refraction because the light ray is perpendicular to the boundary AC. Light rays emerge from air to glass. Here the angle of incidence is 0, because if you draw the normal here, that will be 0. So no refraction. I told when I started this lesson, if the angle of incidence is 0, no refraction. So the light will straightly go into the glass. So there is an angle of incidence here, 45 degree. I calculated it. This is 45 degree given, this is 90 degree, so this should be 45. In this right angle triangle, this is 45, this is 90 degree, this is 45. But this red color line is the normal to the boundary. So this is 90 degree, means this is 45 degree. So 1.52 sine C is equal to the N2, the refractive index of the air is 1. times sine 90. The theta to 90. I'm going to find the critical angle inside the glass. So sine C is equal to 1 over 1.5 to find the critical angle for this glass air boundary. So that is 41.1 degree, 41.1 degree. So angle of incidence 45 degree greater than the critical angle. So total inner reflection will occur. So total inner reflection occur means during total inner reflection all the light will be reflected back according to law of reflection. So angle of incidence is 45. Angle of reflection 45 means 45 with the red color line. With the normal means it must be vertically down here. So this is 45. So the light ray will move vertically down. So when you consider here, again if I draw the normal to the boundary here, this is 45, this is 90 means again this is 45. Again the angle of incidence 45, critical angle is 41.1. So there will be total inner reflection. It will reflect back and it will emerge into air like this. So it will function as act as a reflector. So this could be a reflector. Okay, so the same question now what they are saying, second part, question number 11, second part. Earlier we came across the critical angle, we found it was 41.1, angle of incidence 45. So there will be total inner reflection and the light reflected back and reflected back here, and it reflected back to the air and it functions as a reflector. Now this side AB is covered. Here also the light is same question, so emerging into glass from air such that the angle of incidence is 0 degree perpendicular to the boundary, so no refraction here. The angle of incidence here 45 degree, I already explained in the first part of question number 11. This is the second part. Now this side AB is covered with a transparent sheet of refractive index 1.26. Now what will happen to the light rays? So again we need to calculate the critical angle for glass transparent sheet boundary. Now the boundary has changed. Earlier it was glass air boundary, now glass transparent sheet boundary. So we need to calculate the critical angle for glass transparent sheet boundary. So for glass transparent sheet boundary, so I'm going to use the Snell's law again. N1 sine theta 1 equal N2 sine theta 2. We know still this is optically more denser medium because refractive index 1.52. The transparent sheet 1.26 less compared to 1.52. So this is optically less denser medium. Transparent sheet glass is optically more denser medium. So if there is critical angle that should happen inside the glass, we'll see what could be the critical angle for this boundary now. So earlier it was glass air boundary, now the boundary has changed. So N1 is N glass sine C is equal to N transparent sheet. I'll put NS transparent sheet, NS sheet sine 90. So in glass 1.52 sine C equal 1.26 times sine 91. So sine C equal 1.26 over 1.52. Find the C, take sine inverse, you will get 56 degree. Now what's going to happen? The critical angle for the boundary is 56. The angle of incidence is 45 degrees. So the angle of incidence is less than critical angle. So since 45 degree is less than 56 degree, which is the critical angle, light will emerge into transparent sheet. Earlier there was total inner reflection. Now the light will immerse into transparent sheet. So whenever there's a question like same thing they can ask, light is moving from water to air, the angle of incidence they can give, what will happen to this light ray. So they are also, you need to find the, whenever the light moves from optically more denser medium to less denser medium in a question, they might give the angle of incidence. They can ask what will happen to this light ray. That, what do you mean by what will happen to this light ray? There are two possibilities. One, the light can emerge into the second medium, which is optically less denser medium, or there could be total inner reflection. So in such situation like this type of question, or light is from a fish inside water reaching the water air boundary, they can ask what will happen to this light ray. So they give the refractive index of water. So find the critical angle for water air boundary, then compare the angle of incidence with the critical angle. If the angle of incidence is more than the critical angle, there will be total inner reflection occur. Otherwise, light will emerge into the second medium. Okay, so a glass cuboid is supported. It can't float, but maybe it might be clamped or something like that. It's supported on the surface of water such that the bottom surface is touching water. The refractive index of water is 1.33 and the refractive index of glass is 1.52. So there is an angle, the light is emerged from air to glass. This is the angle theta with the boundary, not with the normal, with the boundary. This is theta. So the light is refracting at the boundary on the surface here and reaching the bottom surface. So the question is, find the maximum angle of theta such that light ray could emerge into water at the bottom surface. Okay, so why the word maximum is used? You know that for the boundary this side, if you use the Snell's law, n1 sine theta 1 equal n2 sine theta 2, n1 theta 1 is with the normal, theta 2 also with the normal. So here when the angle theta increases, when the angle theta, they ask you to find the maximum angle. So that means when the angle theta has a limit, maximum limit, because when the theta increases, theta 1, if I call this as theta 1 here, the theta 1 will decrease. If the theta 1 decreases, inside the glass, the angle of refraction here, theta 2, if I say this is theta 2 also will decrease. Now, when I complete the right angle triangle, extrapolate the normal line here and here. So this is 90 degree. The two normal meet at one point. This is 90 degree. This is a horizontal normal to the vertical boundary. This is a vertical normal to the horizontal boundary. This is 90 degree. So as I told, when the theta increases, it has a limit, that's a question, but anyway, generally we'll analyze first. When theta increases, theta 1 will decrease. When the theta 1 decreases, theta 2 will decrease. When the theta 2 decreases, this angle will increase. So if this angle becomes more than the critical angle for glass water boundary, then the light can't emerge into water. So the idea here, the angle, so the theta can increase, the possible maximum angle is such that this angle is very closer to critical angle, slightly less than critical angle means when this becomes slightly less than critical angle, then the light can emerge into water. Again, I'll explain. When the theta has upper limit, that's a question. Find the maximum, that's a question. Maximum angle of theta. The reason is you can't increase the theta randomly, because if you increase the theta here, theta 1 will decrease because this is 90 degree. So theta plus theta 1 90. So theta increases, theta 1 will decrease. For if I use the Snell's law for this boundary air glass, theta 1 decreases when theta increase, theta 1 decrease, when theta 1 decrease, theta 2 will decrease. This is a theta 2 will decrease. When the theta 2 decrease, this angle, this right angle triangle, total internal angle will be 180, this is 90 degrees. So when this decreases, this will increase. If this increases beyond critical angle, then the light will not emerge into water. So the possible maximum angle of theta such that the angle of this one should not become more than critical angle, at least the critical angle. Then I can find the theta 1 and theta. Okay, so that's the idea. If the light wants to emerge into water, at least this should be slightly less than critical angle. I can take approximately equal to critical angle. So first I need to find the I should use the equation, this one, for glass water boundary. So I want to find the critical angle for glass water boundary. So the angle here should be slightly less than critical angle. I can take almost equal to critical angle. So light is moving from glass to water. Refractive index of glass is 1.52. Optically more denser medium 1.33. Water less denser medium. So that is Ng sine C equal to Nw sine 90. So 1.52 sine C equal 1.33 into sine 91. I'll find sine C equal 1.33 over 1.52. So we'll find the critical angle for glass water boundary. So that will be equal to 61 degree. So if this is 61 degree, now it can't be more than 61. So at least this is 61 degree. This angle, I'll name this angle now, I'll name this as R. This is theta 1. So R should be this in this right angle triangle. If this is 61, not more than 61, so the minimum angle of this one, sorry, the possible maximum angle of this one such that the light emerge into water is 61, can't be more than 61. If this is 61, R will be 90 minus 61, so that will be equal to 29 degree. Now if this is 29, what could be theta 1 angle of incidence in air? So I'll use the Snell's law again for this boundary. N1 sine theta 1 equal N2 sine theta 2, that is sine R I use it, sine theta 2 I am using R, which is now 29 degree. N1 is air 1 into sine theta 1 equal N2 1.52 sine 29. So find the theta 1 here. So theta 1 will be equal to 47.7 degree. So theta max, that's the question, maximum theta. So theta max is equal to 90 minus, so theta max equal 90 minus theta 1, that is 90 minus 47.7 degree. So that will be 42.3 degree. So that's the maximum angle of theta such that the light emerge into water. Okay, next topic is dispersion of white light. You know, white light consists of all colors from violet to red, VIBG, YOR, violet, indigo, blue, green, red, all the colors will be there. You know that frequency of the light never changes when it travels from one medium to another medium. When we consider all the color lights, or different color lights in vacuum and air, or whether we vacuum or air, we treat air and vacuum same, the speed of light is the same. But when we consider different color lights in different media, say for example, when we consider red color, green color, blue color, these color lights in a particular medium such as glass, they won't travel at the same speed, they will have different speed. Remember that red color, blue color, green color, yellow, orange, they all have the same speed when they travel in vacuum or in air. They'll have the same speed, no change among the different colors. But these color lights will have different speed in a medium, in a particular medium. For example, when you consider glass, in which the speed of light of red, green, blue will be different. When light travels from air or vacuum, we treat same. When it travels from air to glass, the frequency remains the same. Frequency of red in air is same as frequency of red in glass, but the speed will different, so wavelength will become different. Therefore, what happens, speed different means different color lights will have different refractive index in a medium. Okay, so we'll think about that way. So this is the prism, we'll consider a prism. Now white light, for white light I'm using black color ink. So this is white light. It will have the same speed in vacuum. The normal I draw by using green ink. This is the normal to the boundary. So when they emerge into glass, they will have different speed. So what happens when you use a prism white light, you can do it at school, your laboratory. When the white light emerge into glass, they will change, they will split because they have different speed inside glass. So you see the red color will come like this. This is the red color, red light. So this is the normal, I draw the normal by green ink. So normal for this side, this is the normal. Then blue color light will, the violet, actually not blue, the violet will come from here. So the red color will be here, violet will be there. So all of the color lights, VIB, GYOR, so violet, this is indigo, that will be, yeah, violet. So VIB, GYOR, this is red. So all of the colors will fall between violet and red. So V, indigo, I, all these colors will be between violet and red. Okay, so all these colors have the same angle of incidence here, I'll make it as I. But when you consider blue color light, this is the angle of refraction for blue color light. So I'll draw a little longer normal. So for blue color light, this is the angle of refraction for blue, and this is the angle of refraction for red, RR. Okay, so what will happen to the refractive index of red and blue? Will they have refractive index different? Yes, they will have different refractive index. Okay, we'll use the equation refractive index, Snell's law, or we'll see simply we can use what we learned in O-level, sin I over sin R. So refractive index of red color NR is equal to sin I over sin red color refractive index RR. Refractive index of blue color NB is equal to sin I, all have the same angle of incidence, sin I over sin RB. But we know that, see the diagram, the blue color, when you do practical, you will get the violet or blue somewhere. Here I'll put violet, sorry, this is not a blue, so I'll put it as violet, NV, refractive index of violet, NV, so this will be NRV, not RR, RV, violet. This is for blue, this is RR, red color. This is for violet, not blue, RV. Okay, so you know that the sign of RR, the angle of RR, the red color refractive index, this refractive angle of refraction for red is greater than angle of refraction for violet. So sin RR greater than sin RV. You can see that sin RR greater than, so you can see the diagram. So this is the angle of refraction for red color, this is the angle of refraction for violet. The angle of refraction for violet is smaller than angle of refraction for red. So sin RR is greater than sin RV. Both have, all the colors have the same angle of incidence. So here when you consider this equation in terms of refractive index, the denominator RR is greater than RV. So denominator greater means NR, refractive index of red, is less than refractive index of violet. This is for violet. So refractive index of violet is greater than refractive index of red color. So different colors will have different refractive index. Also remember that the frequency of red in air and frequency of red in glass is the same. So the speed is changing. So when the speed changes, wavelength will become less in glass compared to wavelength in air. Also, we can conclude. So we found the refractive index of red and violet when we consider in glass. The refractive index of red in glass is smaller than refractive index of violet for glass. So when we use the definition of our glass, NR is equal to speed of light in vacuum. All have the same speed in vacuum or air, all colors. Speed of light in vacuum, which is C divided by speed of light of red in glass. So refractive index of violet is speed of violet in vacuum, that is same as C over speed of violet in glass when we consider. We know that NR less than NV. So NR less than NV means, since NR less than NV means, little mathematics, both have the same numerator CC, but NR less than NV means VR. From this I can say VR greater than VB in glass. So red color will be faster than violet color in glass. Okay, anyway, there are sometimes it could be an MCQ question. So like that, red color has the highest speed or maximum speed in glass than the violet. So compared to red, orange has lower speed. Compared to orange, yellow has lower speed, and so on. Okay, so you can ask me what we learned so far in questions. We say refractive index of glass is equal to 1.52. So this 1.52 or refractive index of water we came across 1.33. So what color for this refractive index we say? Actually that's average refractive index for yellow color. So you can say yellow is somewhere in the mid of these 7 colors, or like average color. So this what we came across so far. Refractive index of glass in a question, if they say refractive index of glass is 1.52 or refractive index of water 1.33, that is for mostly for yellow color. On average, that's for yellow color. Okay, so that's all related to refractive index. So I hope you understood. If you subscribe my lessons, you will receive notification when I upload other videos. So also you can navigate through my playlist to required video. So playlist of the channel, they are all my videos are grouped into different groups, like I already told that when I start this lesson. So by using that, you can navigate to the required video. Bye.